In the last video, we learned the 6 main functions of dplyr, and that brings us a lot of value. Once we want to accomplish things in the real world, we'll have to deviate from the 6 main functions a little bit and learn new functions. Unfortunately, there's millions of new functions, and we're not going to learn them all. What we're going to learn today is not to be afraid of them. We can figure out what those functions do. Buckle up for data manipulation for insight. Things are about to get more intense. Every time we start up R, we want to create a new R script, make sure our working directory is set to our analytics folder, and start from a clean slate. We'll create a data frame of 100 rows with a column named X, and when we print it out, we get too many rows. It's really annoying, especially when you get to 1,000 rows data frames. So instead, we create a tibble, just like a data frame. Tibbles are data frames under the hood with 100 rows, but these tibbles print nicely. And they're just like data frames, but they print better, so we'll use them more frequently so our console doesn't get clogged up with a gazillion rows. Here we learn about slice sample, a function you haven't seen before. If you're curious as to any function, type its name either into the script editor or the console, highlight it, and press function F1, and up comes the help menu. At the top, you see slice, referring to a group of functions with a common naming scheme, slice underscore something else, like slice underscore sample, and the package name dplyr. You'll have to do library dplyr to use this function. The arguments and usage sections of the help documentation detail the inputs we can provide to the function to affect its behavior. For the slice sample function, the .data, n, and prop arguments will be most important. The .data argument is simply the data frame we pass to get a subset of rows. The n argument can specify how many random rows we want returned in our sampled data frame, and the prop argument is a proportion of the rows that we want returned in our sampled data frame. To demonstrate slice sample, we need a data frame. So I will create a data frame, calling it df because I lack creativity at the moment, with 2 columns, X and second column. This data frame has 100 rows, but if I want a random sample of 5, I set the n argument equal to 5. If I want a random sample of 8% of the rows, I set the prop argument to 0.08. And just to reinforce the use of the chaining operator, I encourage you not to put the data frame as the first argument inside the slice sample function, but rather to take it out of the slice sample function and use the chaining operator to pass it in as the first argument. It creates much more readable code. Position your cursor anywhere among the chained functions and press Control Enter, and it executes, returning the 8 rows on the bottom of the screen. You may have noticed that every time I ran slice sample, I got a different set of rows as output. There's randomness to the behavior of slice sample. In teaching analytics, I often want your randomness and my randomness to match up. In order for us to both get the same random sample, I use the SetSeed function, pass any integer as an argument, and as long as our integers are the same, every time I run lines say 6 through 8 here, I get the exact same results. If I were to run just lines 7 and 8 without running line 6 first, I'm back to getting random results. That will vary from computer to computer. When I ask you to use SetSeed, make sure you execute it immediately before executing a function that has random output. We learned filter to get a subset of rows, then we learned slice sample to get a random subset of rows. Occasionally we will want to get all the unique rows, and that is where the distinct function comes in. Just like filter and slice sample, pass it a data frame, it returns all unique rows. Here I create another unique data frame called df2 with 2 columns, one called name and one called age. You will see some of the names are repetitive and some of the ages are repetitive. Ultimately, when I look at this data frame, it is a 5-row data frame, but we could see that rows 1 and 3 are duplicates of one another. Despite Bob and Charlie having the same age, they are not duplicates because they have different names. Despite there being 3 Adams, only 2 of them are duplicates because they have different ages. Straight up, people, working with dates is a pain. Let me give you an example. We're going to add 4 appointment dates for Adam, Bob, and Charlie, or the 2 Adams, Bob and Charlie, right? We have 2 different aged Adams. So they have appointment dates in the future. 2 of them are 2021, then the third guy's 2020, and the fourth one is 2021. So to us, these dates have meaning. As we print them out, though, we can see that the dates are not in order. We want to rectify this situation. Fortunately, we learned the arrange function from the dplyr package, but the dates are not in order again. What gives? Why is November 22nd, 2021 coming before November 6th and November 7th? This really is not good. We turn to the lubridate package to say, hey, R, this vector of dates that I gave you, you're interpreting them as a character vector or string. I don't want to alphabetize the text in these strings. They're actually dates. So from the lubridate package, we get the MDY function standing for month, day, year, meaning the input is given in some format where the first number is month, the second is day, and the third is year. Changing the appointment date so that it is now a date vector instead of a character vector then allows us to arrange the dates in ascending order just the way we want. As I've alluded to, in R, the data frame is the main R object we work with as business analysts. Sometimes, though, the information we want to access is spread across multiple data frames. To consolidate all that information into one data frame, we use the left join function. Here, we set up a patient appointment data frame consisting of the names and ages of our patients, as well as their appointment date sometime in the future. We can then have a calendar data frame, and I'm setting it up here as a tibble, specifying the dates the office is open and which doctor is working on that date. For illustration, I will only include 2 dates, November 6th and November 7th of 2021. And the doctors working on those days, we have Dr. Aaron on November 6th and Dr. Alero on November 7th. A reasonable query to ask at this point is, what doctor is associated with each patient's appointment? In our patient appointment data frame, we see the appointment dates. Notice Adam and Bob are the 2 on November 6th and November 7th. What doctor will Adam and Bob have on those days? Well, it's easy to look at the data frame above and say November 6th is Dr. Aaron, so Adam will have Dr. Aaron, and November 7th is Dr. Alero, so Bob will have Dr. Alero. And Charlie, well, I don't know who his doctor is because we don't have an assignment for that date. To make things a little easier to view, I'm going to put the console from the bottom left and put it on the right-hand side and have the script editor take up the entire left-hand side of the RStudio user interface. So to start a left join, start with the table where you want 0 of the rows to be removed. You want to keep all the rows in the first table. That's called the left side table of a left join. In this case, patient appointment DF with 4 rows. We want to keep all those 4 rows, yet we want to bring in the calendar of doctors assigned to dates, which is calendar DF, using this left join. Notice that the date column in patient appointment DF is called appointment date, yet the date column in calendar DF is just called date. We need to make sure that R is told that these 2 columns are equivalent. When columns share the same name, it will just assume those are the columns you want to join by. But in the case that columns are not named the same thing, in this case date and appointment date, we have to be explicit about it and use the by argument with the left table's column name on the left and the right table's column name on the right. The last function we'll look at is the end function. It's an example of a summary function. Summary functions take vectors and collapse them into one value. The end function is used in combination with dplyr to count the number of rows in a group. So let's take the patient appointment data frame we made earlier and count the number of times a name appears. The workflow to do this is group by name, and nothing changes when we do Control Enter and see the output. But then when we summarize the 1-2 punch, remember 1-2 punch, group by summarize, when we summarize, and we'll call this new summary column number of appointments or num appointments, we can use the end function and it will simply count the number of rows inside of each group. And since grouping is done by name, we get the 3 names with the number of appointments by group. A typical workflow now is you might want the proportion or the percentage of appointments taken up by each name. We add a third punch. First punch is group by, second punch is summarized, and the third punch to get percentages is a mutate command. And we define a column, percentage of appointments, that equals num appointments, which is the vector you see in the bottom left, 211, divided by the sum of num appointments. Well, the sum of num appointments, since it's a summary function, collapses that vector, 211, into a sum, which is 4, 2 plus 1 plus 1. Since num appointments is a 3-element vector, 211, each element then gets divided by 4. This is called vector recycling. Since sum of number of appointments is only a single number, 4, it gets reused for each of the elements in num appointments. You will use this workflow a lot throughout this course, so rewind this section, go through it slowly, pause, and make sure you digest what is being done with the end function. The amount of functions in R is overwhelming, so it's often good to use cheat sheets to find functions, the RStudio cheat sheets. A good workflow also is to use Google. Here we find unique rows of a data frame, and we get some search results. I'll give you a little secret. The easier way to do things in R is to always use the tidyverse method of doing things. So add tidyverse to your search term, and you'll get results that are probably easier to follow and easier for you to work with, especially when going through this course. The RStudio cheat sheets are also very useful. In fact, for the dplyr chapters, all you need is the dplyr cheat sheet functions, and that will give you everything you need to do to manipulate data. Here's goes by the Lubridate cheat sheet, but that will give you everything you need to do in terms of manipulating data and getting it in the right format. So here's the dplyr cheat sheet. It says the data transformation cheat sheet, and every data manipulation function you will need to work through this course is contained right within this cheat sheet. Bring it to bed with you and study it. Now let's take some of the functions we just learned and put them to good use. We'll do some data manipulation for insight. The Zaptec firm sells 4 product categories. The category manager of the marketables category insists that they sell more than 60% of all units shipped from Zaptec. The other product categories are in disbelief. They don't believe it's true. Well, let's turn to the data. We start our R session in the typical way, making sure we take ownership of our working directory and know where our files will be read and write to as we save our scripts. We open up a new R script and we can start our analysis. So our motivating question is, what percentage of units shipped come from the marketables category? Luckily, ZapText data is built into the Causact package. We see 117,000 plus rows of shipment data. Each row contains part IDs, but no product category information. The product category information lives in a different data frame, ProdLineDF. We can see that ProdLineDF associates part IDs with product categories. To combine these two tables, we use the left join that we just learned. We want to keep every row from DeliveryDF or DelivDF and join it to the ProdLineDF information to get product category information. We're going to use the 1, 2, 3 punch of group by, summarize, and then mutate, or a percentage of units shipped, to get a percentage of units shipped by product category. We group by product category. We then summarize the information by unit shipped. We see there's an NA product category, which it turns out is not products but actually services that are sold, so we eliminate it using the filter function. Not is.na means not NA, so we keep the units that are not NA. We then mutate and do our little trick of vector recycling to get the percentage of all shipments belonging to the marketing category and discover that it is indeed greater than 60%. That product category manager was correct in their assertion.